This is my last week lecture. Yeah. So time flies for this course. Yeah. Okay, last week we have learned control flow graph, and I have given you a set of rules to apply. Okay. This rule will work for all structured pseudocode. And all the code you are going to see for quiz and exam will be in structured pseudocode. So you can apply this set of rules to cut a program, to cut a piece of pseudocode into basic block. Because in the control flow graph, a node is to represent a sequence of statements. A sequence of statements. This is a sequence of statements. During program execution, always execute from the first statements, statement by statement, until the last statement without any jumping. So that is the property of basic block. So it is very important to identify basic block correctly when you draw control flow graph. All right. So we have seen this example, and I have also highlighted to you that if you try to combine the first four statements together as a basic block instead of just have three statements, instead of just having three statements, you combine the fourth statement together with the first three statements. Then this sequence of four statements will no longer be a basic block, because during program execution, you will not always execute from the first statement, statement by statement, until the last statements. The reason is that when you go through the loop, when you reach here, you will come back here. You will start from here in terms of this sequence. You will not start from the first statements. All right? So, but when you use a rule, those basic blocks you identify are the maximum basic block. That means they are the maximum sequence. You cannot extend it any further. If you try to extend it further, definitely will be wrong, will not be a basic block anymore. But when you use a rule to cut the piece of pseudocode in this basic block, if you further divide it, they say the first three statements, if instead of three statements, you try as a block, as a basic block, you try to divide, you try to put the first two statements, okay, as a basic block. That is okay, okay? So during program execution, you will always start from here, and as this is a sequence, the first two statements as a sequence during program execution, we always start from here and statement by statement until the last statement, okay? And if you divide into two, this statement alone will also form a basic block, okay? If it's anyway, a sequence of one statement will always be a basic block, because when you execute, you have to start from that statement. When you exit, you have to be from that statement also, because it's only one statement. So a single statement sequence will always be a basic block, no matter how. Then why don't we represent every statement as a node then, since it is definitely a basic block? Because by doing so, your control flow graph will be too big. Will be too big. Okay? So then for a complex case, it will be not manageable. Okay, this slide, the example in this slide, the control flow graph, I will leave it to you to go through. All right, there's only one point I would like to highlight here is that in this case, I purposely divide a basic block by using the rule to cut, by using just now the rule I show you to cut, okay? These two statements, that means the statement represented by block 3 and block 4 should be together, I purposely divide it into two, okay? By doing so, it's okay. The control flow graph will be okay. It's slightly bigger, that's all, okay? So when we use the rule to cut a piece of pseudocode into basic block, you can further divide them. You can further divide those resulting blocks. It will still be basic block, but we don't want to do so because by doing so, the control flow graph will be too large, difficult to handle, to deal with. All right? So the detail of this control flow graph, I will leave it to you to go through. I put a 1 here means that sequence 1 have 2 statements. This one is statement. Okay? I put a 2 here means sequence 2 start from here and here. Okay? Until the sequence 3 start, etc. So you go through yourself. Okay, after learn the control flow graph, the next thing we are going to do is to study the 3 basic structural testing techniques. So from this slide onwards, our focus is to study 3 basic structural testing techniques, to learn their basis and to know how to apply, okay, to design test cases, to test a piece of code. By the way, all the structural testing techniques, okay, design test cases from the analysis of code. Okay, these are the 3 basic structural testing techniques we want to learn: statement coverage, branch coverage, and basis path coverage. So we will start from statement coverage first. Each of them have an objective, okay, to in terms of the code, Okay, the objective of statement coverage is to design a set of test cases. The objective of statement coverage, from the name apply, from the name you can see that it is to design a set of test cases. A set of test cases is a test suite. Okay? A test suite is a set of test cases. So the objective of this is to design a test suite to exercise each statement in the program at least one. Okay, so that's why we call this one a statement coverage testing. So the objective of this one is to design a test suite to ensure that by executing the program using the test suite, using the test cases, we will execute each and every statement in the program. Okay? So that is the objective. So targeting a statement, individual statements. A basic block is a sequence of statements that always execute from the first statements, statement by statement until the last statement. So to exercise each statement at least one is equivalent to exercise each basic block at least one. So how to design a test suite to exercise each basic block at this one? That means to exercise each node in the CFG at least one. Okay, this is CFG, the one we have constructed earlier. Okay, to exercise each statement at least one means is equivalent to exercise each node. Each nodes means each basic block at least one. Okay. Firstly, I would like to highlight to you that, okay, during program execution, when you execute a program once, you will definitely follow a path through the control flow graph. Every time when you execute a program, you will follow one path in the control flow graph. You will execute a program following one path in the control flow graph. So in this program, This irritating pop-up. Okay. Every time when you execute a program, you will exercise look like it has not given up yet. Okay. Hope that you will give up. Yeah. Okay. Every time when you execute a program, you will certainly follow one path in the control flow graph from the first node until the exit. This is the entry, this is the exit in this control flow graph. So either follow this path, in other words, or follow this path, go through until from entry to exit, or follow this path. This way, then get back again, go through one more time, then exit, okay? So every time when you execute a program, you will certainly execute the program following one path through the control flow graph. Okay. So the objective of statement coverage is to design a test suite, to design a set of test cases, to make sure that by running through all the test cases in your test suite, every node will execute at least once. Okay? So that's the objective. So how to design a test suite to ensure that every node is exercised at least once. Executed means exercise at least once. Okay, so very simple. The first thing is you go to the control flow graph. After you draw the control flow, you go to the control flow graph to find a set of path. Okay? To find a set of path, pass through all the nodes. To find a set of path, okay, as the whole set, the path together pass through all the nodes. Okay? So the first thing is to identify a set of path. Then after that, for each path, okay, you analyze the code, analyze the condition to find input value, okay, to ensure that by using the input value, the program will exercise the path. Okay? So the second step is something like solving simultaneous equation in mathematics. Okay? So the first step is to find a path, find the set of path. The second step is something like solving simultaneous equation in mathematics. I will show you soon. Okay? So that means if you have 5 paths, then you will design 5 test cases for your test suite. Right? So of course, for the exercise purpose, in order to understand it, we will do it manually. We will do this manually. But in practice, if you want to apply such testing techniques, normally you will need to use automated tool because a piece of code can be quite large and it's quite impossible to do it manually in practice. You will have to use some testing tool to do it. Okay, now we look at this simple piece of code. Okay, we have already constructed a control flow graph earlier. Okay. So now we want to apply. Now I show you how to apply statement coverage testing techniques to design a test suite. Okay. So in this slide, we only write down the answer. The explanation is written in the subsequent slide. Okay? The explanation is all written here. Firstly, we find a set of paths, okay, to pass through all the nodes. Okay? So this is the set of paths I have found. 1, 2, 3, 4, 6, 2, 7. 1, 2, 3, 5, 6, 2, 7. Okay? So having these 2 paths to form a set, my set of paths has passed through all the nodes. 1, 2, 3, 4, 6, 2, 7. Okay, this is one path from entry from the first node to the last node. So every path have to start from the first node to the last node. Okay? So the first path pass through how many nodes? One path. The first path alone, does it pass through all the nodes? No. The first path pass through almost all the nodes except node 5. Okay? So one path is not enough. I have to introduce some more path in my set. So the second path I introduce is 1, 2, 3, 5, 6, 2, 7. Okay? So by having these two paths together, I have a set of paths pass through all the nodes. So very straightforward, pass through all the nodes. Okay, now this is so I have found the set of paths, okay, for statement coverage testing. The next thing I need to do is for each path, for each of these paths, that means altogether are two paths. Okay, I have to examine the code, examine the control program, examine the code to find the input value. Okay, to ensure that by using the input value I design, the program will execute through this path. The first path is here. Okay, I have to find input by going to the control program and examining the pseudocode. I need to find input value to ensure that during program execution, okay, my input will make the program execute this path 1, 2, 3, 4, 6, 2, 7. Okay, so I go back to the code. 1, 2. Okay. From here, from this piece of code, you can see that read IY. Read means input. So in this case, there are two input variables, I and Y. I and Y. So that means I have to find the value of I and Y to ensure that the program execute through this path. Find the value of I and Y. Okay. So until to execute the first node, there's no problem. Okay. All input will start from the first node. Okay. But when it comes to second nodes, I have to be careful. Okay. In order to go through here, now my path is 1, 2, 3, 4, 6, 2, 7. In order to go through here, I have to make this condition satisfied. Okay. If it's not satisfied, you will go to here. So I have to ensure that this condition is satisfied. That means I have to choose a value, I less than 100. Okay? I have to choose a value, I. Okay? As far as it's less than 100, you will make the program execute through this branch, and that is my path. Okay? My path follow this branch. Okay? So I have to be less than 100. Okay? In this case, I choose 99. That's why I choose 99, because it have to be less. You can choose, if 98 is suitable, you can choose 98. Okay? As far as now, as far as I is less than 100 is okay. But when I come here, this is my path, 1, 2, 3, 4, 6, 2, 7. When I come to 3, my path follow this branch, 3, 4. So that means I have to, at this point, I have to make sure that this condition is true. This condition, this if condition is true. Okay? Have to be true. In order for this one to be true, y have to be less than 0. Y have to be less than 0. You can see that if y less than 0, then this condition is true. So it will follow this branch. So I have to choose a y less than 0. In this case, I choose -1. All right? So followed here, so to make sure the program execute following this branch, that is my path. Then after that, when you come here, okay, no problem. Need not to, it will not affect the value. It does not require any special condition on I and Y. So that come here is okay as well. So when you reach here, have to be careful with 2, 7. Okay. So the second time when you reach here, I have to make sure that this condition 2 is this one statement. I less than 100 should not be true. It should be false, because if it's true, you'll go through here again. So I have to make sure that the second time when you reach here, I have to be I cannot be less than 100. Okay, so since the second time when I reach here, I cannot be less than 100. Okay, so I choose I equal to 99. Okay, so it satisfied it satisfied this branch when I first pass through to node 2. Okay, subsequently when it come here, I will increase. Okay, when you go to 6, I will increase. 99i plus 1 become 100. Okay, so these nodes will define I to 100. So when you come here again, I already exceed. I is already 100, so it's no longer less than 100. So it just nice satisfy this condition. You will come out from here. Okay, so that is the way to choose value I and Y. Okay, after you choose the value I and Y, then you go back to the pseudocode to compute the result, compute the expected result. In this case, since print AB, that means AB output value. So I have to compute the value I, A, and B according to the code. According to the code, go back to the pseudocode to compute the value for A and B. Okay, when I equal to 99, Y equal to -1. Compute accordingly. In this case, you can compute easily. It is A equal to 2, B equal to 2. So that is the way to find input value. When you have a path, that's the way to find input value. Okay, to ensure that it satisfies all the conditions of branches that the path pass through. Okay, and when you try to determine the value of A and B, you have to consider whether in between the value of input change or not, as this case. Okay, when you come here, although initially I set it to 99, when you come here, I change to 100. So when you go back, I become 100. So just 9, just satisfy the condition. And this is important. Later, when we learn branch coverage testing techniques, and we learn basis path coverage testing techniques, okay, when we have a set of path, after you have a set of path, for each path, we still follow this method, okay, to find the value of inputs, okay? And after you find the value of input, the output, you will just go to the pseudocode to compute accordingly. Okay, so that is straightforward. Okay, here there's another statement here saying that this is not a minimum test suite. Okay, this particular test suite have 2 test cases. Okay, so what for? I will not go through the second path. Okay, I will not go to the second path. The way to design to find input value is exactly the same. All right. So in this case, I have the first one. In order to exercise this path, I will definitely have to be set to 99. Okay, but Y doesn't matter. You can choose -1. You can choose -2. There's a lot of value for Y that you can choose. Okay, this here say that this particular test suite that has 2 test cases is not a minimum test suite. A minimum test suite means a test suite with the least number of test cases. Okay, for statement coverage testing, a test suite that has the least number of test cases for statement coverage testing. But the statement here says that this is not a minimum test suite. That means this test suite does not have the least number of test cases for design from statement coverage testing. That means, what does that imply? That means we can actually design a test suite with only 1 test case, okay, for statement coverage testing. Okay, very straightforward. Anyway, here there's a loop, right? Here there is a loop, so we can have a longer path, 1, 2, 3, as such. 1, 2, 3, 4, 6, 2, 3, 5, 6, 2, 7. That means 1, 2, 3, 4, 6. When you come here, we don't get out. We go through again. The second time come here, we follow the other branch. 3, 5 instead of 3, 4. 6, 2, 7. That means go through this loop 2 times. The first time follow this branch, the second time follow the other branch, okay? So by having this path in our set of path, straight away one path pass through all the nodes. So you need not to introduce any more path to your set, okay? So we have a single path set. Then since you have only one path, that means you need to design only one test case, right? So we will have a test suite with only one test case for statement coverage testing. This is the minimum test suite. Okay, the detailed step is shown here. Okay, so after you have the set, it's the same. You go back to the control flow graph and examine to ensure that in order to exercise this path, you have to go back to the control flow graph, go back to the code to ensure that, okay, all the branches that the path pass through, to ensure that, okay, your input satisfies the condition of all the branches that the path pass through. Okay, this path pass through how many branches? 1, 2, 3, 4, 6, 2, 3, 5, 6, 2, 7. How many branches in this control flow graph? Okay, all the outgoing edges at decision node are branches. We have 2 decision nodes here. This decision node, right? So this one, and this one are branches. All together 4 branches. And the path I have just read out. 1, 2, 3, 4, 6, 2, 3, 5, 6, 2, 7. Okay, pass through how many branches? Pass through these branches twice, 2 times. And pass through this branch 1, and this branch 1, and this one 1 also. Okay? So all these are branches. So you have to go back to the code to make sure that all the branches that the path pass through, to ensure that your input satisfies the condition of all the branches that the path pass through. Okay, so define the input value. After you have defined the input value, then you substitute the input value to the pseudocode inside the pseudocode and to compute the output value accordingly. Okay, now we come to branch coverage testing. Earlier on, we learned the concept of decision nodes. So a decision node is a node in the control flow graph with more than one outgoing edge. Okay? Any nodes that have multiple outgoing edges are decision nodes. So in this control flow graph, there are 2 decision nodes, here and here. These are the 2 nodes have multiple outgoing edges. Each of them have 2 outgoing edges. Okay, 2, 3 are the decision nodes. So, okay, so what is a branch in the control flow graph? A branch is an outgoing edge, okay, at decision node. A branch is an outgoing edge at a decision node. Okay, so these 2 are decision nodes. Okay, all the outgoing edges at decision node are branches. So how many branches? 2, 3, 2, 7, 3, 4, 3, 5. Altogether, there are 4 branches here. 4 branches. So you have to understand the meaning of branches, the meaning of decision node before we can study branch coverage testing. Branch coverage testings have a different objective, okay, from statement coverage testing. Statement coverage testing is to ensure that, okay, our test suite exercise each and every statement at least 1. That means to ensure that our test suite exercise each and every node at least 1. But branch coverage testing is to ensure that our test suite exercise each branch at least one. Okay, so now branch coverage testing, we aim at branch. That's how the name comes from. Okay, to ensure that our test suite exercise each branch at least one. So the way we design test cases is quite similar to statement coverage testing. So the first step is to find a set of paths to pass through all the branches in our control flow graph. So for this graph, mean to find a set of paths to pass through all the 4 branches that I have just read up just now. This is the first step. Okay. So after you have find a set of paths to pass through all the branches, the second step is exactly as what we do in statement coverage testing. That means for each path, we go to the control flow graph, to go to the code, to find input value, to ensure that all the condition of branches that our path follow are satisfied. Okay. To ensure that all the branches that the path follow are satisfied. Okay. So that is the way. Again, for this control flow graph, I have designed a set of test cases. The set of test cases is written here, and the explanation of how to design, okay, is written in the next slide again. These are the 4 branches, okay? So now I have a set of paths to pass through all the branches. 1, 2, 3, 4, 6, 2, 7, okay. This path pass through how many branches? Pass through 3 branches out of 4, except this branch does not pass through. 1, 2, 3, 4, 6, 2, 7. Okay, pass through all the branches except this one. So this path alone is not enough. So I introduce a second path. 1, 2, 3, 5, 6, 2, 7. So the 2 paths combined together pass through all the branches. Pass through all these branches in the control flow graph. Okay. So after you have a set of paths, the next step is exactly the same as what we do in for statement coverage testing. For each path, okay, we go to the control flow graph and go to the code to find input value I and Y to ensure that, okay, our input value satisfies the condition of all the branches that the path pass through. The condition, every branch have a condition. Okay, 2, 3, in 2 come to 3, I have to be less than 100, etc. Okay, so this to ensure that it satisfies all these conditions. So, in fact, the path I have chosen here is exactly the same. The set of path I have chosen is exactly the same with the one we choose for statement coverage testing. Okay, so in this case, the same set is fine. We can use the same set for branch coverage testing. That is not always the case, but in this case happened to be fine. Okay, and here highlight that this is not a minimum test suite, because not minimum test suite, that means this particular test suite does not have the least number of test cases, okay, for branch coverage testing. Okay, so since now we have only 2 test cases, and it does not have the least number of test cases, that means actually we can have only 1 test case, okay, for branch coverage testing. Again, the detail, okay, how to construct a minimum test suite for branch coverage testing is written down here. I will leave it to you to go through. Okay, now we come to a concept here, the relationship between branch and statement coverage testing. Branch coverage testing always implies statement coverage testing. That means when you have a test suite for branch coverage testing, your test suite will always be good. Will also be good for statement coverage testing. Okay, they can be used for statement coverage testing techniques also. Okay, because branch coverage testing is a stronger conditions. because every statement certainly follow under one branch. That is why. But the other way around, if you have a test suite for statement coverage testing, okay, that may not be good enough. In general, that may not be good enough for branch coverage testing. This example show you that, okay, a very simple piece of pseudocode. Okay, we have only 3 nodes, okay, and in this control flow graph there are 2 paths only. This path from the first node to the last, and this path. Okay, there are only 2 paths. Okay, and if we design a test suite using statement coverage testing, we can design just one test case. Okay, our test suite can have just one test case because having one path will pass through all the nodes. Okay, one path can pass through all the 1, 2, 3. This path. Okay, in order to exercise 1, 2, 3. Okay, this is the test case that we can design. But this test suite is not good, is not correct for branch coverage testing because this particular test suite, when you execute it, does not exercise each branch at least one. Okay, there's another branch here. In this case, there are 2. Node 1 is a decision node because have two outgoing edges. There are 2 branches. One here, 1, 2, and the other one is 2, 3. This particular test suite only exercise 1, 2, 3. Only exercise the first branch. It does not exercise the second branch, 1, 3. Okay, so this test suite for statement coverage testing is not good enough for branch coverage testing. Okay, branch coverage testing is a stronger conditions. Okay, now we come to the last testing technique. That is basis path testing. So, statement coverage testing aim to exercise each node at least one. Branch coverage testing aim to exercise each branch at least one. And basis path testing techniques have a different objective also. Okay. In general, it is not possible to cover all the paths through a control flow graph. In general, okay. Of course, in this case, you can have 2 test suites to exercise all the paths because there are 2 paths only. 1, 2, 3. 1, 3. Okay, you can only have 2 paths in this. There are only 2 paths in this control flow graph. But for the other one, for this one, okay, we have infinite number of paths. 1, 2, 3, 4, 6, 2, 3, 4, 6, 2, 3, 4, 6, 2, 3, 4. Continue. Yeah. You can repeat this loop many times. Okay. So come up with a different path. So how many paths in this control flow graph? We have infinite number of paths in this control flow graph. Infinite number of paths. You can repeat the loop 2 times, 3 times, 100 times, 1,000 times, 2,000 times, 1 million times. So we have infinite number of control paths through this control flow graph. So in general, it is not possible, it is impossible to exercise each and every path at least one. Okay? And basis path testing techniques is aimed to address this particular issue. So the basic idea behind the basic path testing is to identify an essential set of paths. Okay? Since there's no way for us to exercise each path at least one, so in basis path testing techniques, we want to exercise those important paths, okay, those important paths, those independent paths, at least one. Okay. Since there's no way to exercise each and every path, then we focus on exercise those important, those independent paths. That is the objective of basis path testing techniques. Okay. Then once you identify a set of independent important paths, then we will design a test suite to exercise each of them. In practice, we also need automated tool to carry out basis path testing techniques. Okay, there are 3 steps in basis path testing techniques. The first step is to compute cyclomatic complexity, okay, Vg, this notation for cyclomatic complexity, V bracket G, the whole thing together is a notation, equal to E minus N plus 2. Number of edges minus number of nodes plus 2. Very simple formula. Okay? So you should be able to remember. It's very simple formula. Yeah. I can remember too. Yeah. So after you have compute this number, after you construct the control flow graph, we compute this cyclomatic complexity. After you have computed the cyclomatic complexity, then this number will guide us to identify a basis set of linearly independent paths. Okay? We do not aim to identify all the paths. Okay? We identify a basis set of linearly independent paths. Okay? The term is come from linear algebra. Okay? For those of you study linear algebra before, this term is come from linear algebra. So we identify a basis set of linearly independent paths from the control flow graph, from the CFG. Then after that, we design a test suite to exercise each and every path, okay, in our basis set of linearly independent paths. By the way, here is to highlight to you that basis set of linearly independent paths is not unique. Okay? In linear algebra, when you compute a basis set, okay, it's also not unique. So our basis set of linearly independent paths is not unique. That means you may identify a basis set of linearly independent paths from the control program. I may identify another one, and both answers could be correct. Okay, so it's not unique. But we will always have the same number of paths. Okay, the number follow Vg, follow cyclomatic complexity. So the first step is to compute a cyclomatic complexity. Okay, we use this one as an example to show how to compute Vg, cyclomatic complexity. Okay. So these are number of nodes. 1, 2, 3, 4, 5, 6, 7, 8, 9. Number of nodes. Okay, number of edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Altogether 11 edges. Okay, don't be confused by this part. Over here, an edge means a connection between two nodes without passing through another node. So this is a connection between two nodes. This is a connection between two nodes. This is a connection between two nodes. Okay, nothing else. Okay, there are three connections between two nodes over here. So don't get confused. Yeah, with this part. That's all. This control flow graph is slightly different. Okay, so after you calculate this number, that means the next step, when we identify a basis set of linearly independent path, we should have 4 paths. We should have 4 paths. Okay, so this number guide us. Before we go further, here is to highlight that in general, you do not need to design program with very high cyclomatic complexity. The program with very high cyclomatic complexity usually will be more complex and introduce more error. And in general, you can minimize the cyclomatic complexity when you design a program so that your program will not be so error prone. Okay, now we come to the second step, how to identify a basis set of linearly independent paths. Firstly, okay, this is an important step. When we identify a basis set of linearly independent paths, firstly, we construct our set, okay, one by one. We introduce path. Based on the control flow graph, we include path in our set one by one. We include a path from start to end, okay, one by one in our set. Firstly, we include the shortest one. Okay, like this case. Firstly, we include the shortest one. Path 1. Okay, 0, 1, 2, 3, 4, 7, 8. Okay, this is the shortest. Firstly, we include the shortest one. After we include a path in our set, we will go back to the control program to check whether the set of paths we have constructed so far pass through all the nodes and edges. If it has not passed through all the nodes and edges, we have to continue. Continue to add path until our set of path has passed through all the nodes and edges. Okay. How to add in the subsequent path? Okay. Every time when you want to add in the next path, if we need to add in the next path, you will follow the previous path. Make a minimum change to the previous path. So the first path I include is here. After you have included the first path, there's a lot of nodes and edges we have not passed through yet. So we continue to add in the next one. The next one, we make a change. 0, 1, 2, 3. Instead of go to 4, we make a change here. We go to 3. 0, 1, 2, 3. When we come here, okay, after you make a change, you should follow the previous path, if you can. But if there's no way for you to follow the previous path, you have free of choice. You can choose any of them, okay? So since after you make this change, there's no way for you to follow the previous one. Because the previous one, after go to 3, you go to 4, then come here. There's no way. So we choose this one, 2, 3, 6, 7, 8. Okay, this one is the second path, okay? So when you come here, 7, when you come here, you have to go out 8, okay? Because at this point, you can follow the previous path. You have to follow. That means minimum change means after you have made a change, you have to follow the previous path unless there's no way for you to follow. Then you have free of choice. Like this case, when I make a change here, there's no way to follow. That means the second path, I can choose 3, 6, 7, 8. I can also choose 3, 5. Both are fine. Both are fine. So after I have the second path, again, I go back to the control program to check whether has my set of path passed through all the nodes and edges. Okay, still not. We have not passed through node 5 yet. Okay, so that means we have to continue the add in path. So I add in the third one. The third one, I have to follow the previous one, the second one. I make a change here. Instead of go to 6, I go to 5. Then after that, follow. After make a change, I have to follow strictly. Okay? So I have the third path. After you add in the third path, we have passed through all the nodes. But we have not passed through one edge yet. This is the edge. This is the edge. 7, 2. Okay, we have not passed through this 7, 2 yet. So we have to continue to add in. Okay, because our set of path have to pass through all the nodes and edges. So I add in the fourth one. 0, 1, 2, 3, 5. Follow the previous path. Now, instead of going out here, I make a change here, come to 2. Okay, come to 2. After you make a change here, again, there's no way to follow the previous one. Follow path 3. So I have free a choice. That means this path I can go through here, I can go through here, I can go through here as well. But when you reach 7, you have to go out to 8. Okay, so there's a minimum, meaning a minimum change. In other words, when you, okay, after you add in the last path, you find that you have passed through all the nodes and edges. Okay, so that means we have completed the construction of our set of path. We stop, then we design a test case to exercise each of them. This one is exactly the same as statement coverage testing and branch coverage testings. Okay, so minimum change means after you make a change, you have to follow the previous path. For example, after you make the second path, after you make a change here, then when you reach 7, you can follow the previous path. I have to follow the previous path 7, 8 out. I cannot make the second path 7, 2. Okay? Then it's no longer a minimum change. If your second path becomes 7, 2, okay, because you have already made a change here. And when you reach this point, you can follow path 1. So you have to follow. That is the meaning of minimum change. And this is the important point. Okay, I think today I stop here. we have one more example to go through. Tomorrow I will go through this example, right? Okay, see you again tomorrow.